So yesterday in class we went over doing quantitative energy problems to figure out how much energy would be required to warm something or how much energy would be removed to cool something, and then energy required to go through phase changes. We did those questions, but they only involved one step. Either was a solid warming or cooling, a liquid warming or cooling, something melting or freezing, or something evaporating or condensing. Just one thing. Today we're going to be looking at when you have multiple changes happening. Okay, so we're going to do questions 1 and 2 on the new assignment. The rest of the assignment is due for tomorrow. We'll be whiteboarding and going over them. I've left an answer key so you can find out if you did the problems right or not. But we're going to do questions 1 and 2. And the process is exactly the same. We start with doing a heating curve for the question to help us figure out what it is that we need to do. So question 1 says, how much energy must be absorbed by a 150 gram sample of ice at 0 degrees Celsius that melts and then warms to 25 degrees Celsius? So if we make our little heating curve thing over here, energy down here, it starts out at 0 degrees Celsius. So the whole sample of ice is at 0 degrees Celsius and it's going to melt. And as we've talked about, when something melts, only the interaction energy is changing and not the thermal energy, so the temperature remains constant until it's done melting. And then it's going to go up to a final temperature of 25 degrees Celsius. So what do we have here? We have the ice that's melting. We have the liquid that is warming. Now, when we whiteboarded the LOL diagram assignment last week, one of the questions that I asked a presenter was, when we have things like warming and then boiling, or melting and then warming, do these changes happen all at once, or do they happen in a specific order? These things, and we saw this in the Icy Hot Lab too, they don't happen all at once. If we look at this graph, what has to happen first? The melting has to happen first. That's step 1. So all the ice has to melt, and then in step 2, the liquid warms. So when it comes to solving a question like this, we have to take it in steps. Treat it as separate problems, and then figure out what we need to do from there. So in this question wants to know the total amount of energy needed. So if we figure out the energy required for the melting portion and the energy required for the liquid warming portion, we can just add them together and get the total amount of energy, but we have to take it in steps. So step 1 is when the ice cube is melting. And for that, I'm going to use the equation, the energy equals the mass times the heat of fusion. And that's 150 grams times 334 joules per gram. So we're talking about solid water. And so that energy to the right number of sig figs comes out to 5.0 times 10 to the 4th joules. In other words, 50,000 joules. I write it in scientific notation because to get it to 2 sig figs and show that it's in 2 sig figs, we'd have to have it in scientific notation. So that's step 1. In step 2, now it's all melted, and we're dealing with a liquid that is warming up. So Q equals mass times the heat capacity times the change in temperature. It's still 150 grams. Law of conservation of mass, the mass before and after a physical change or chemical change, in this case physical, remains the same. 4.18 joules over grams degrees C times the temperature change. The final temperature is 25.0 minus 0, which was the initial temperature. We can see that from our graph during this section here. It starts at 0, ends at 25. So 25 minus 0. And if we calculate that out to the right number of significant figures, we're going to get 16,000 joules. So it took 50,000 joules to melt it. It took 16,000 joules in order to warm it up. And since we want to know the total energy. We take the 50,000 joules and the 16,000 joules, and we add them together to get 66,000 joules. So one variation on these questions is just to find the total energy change for each step, but it's super important. Do this diagram first. Figure out what things are happening in what order so that when we start to actually solve the problem, we can do each step separate and in order. Okay. You can't have just the liquid melting, or excuse me, the liquid warming. Okay. It's two separate steps as shown in that graph. So that's one variation on the question. Another one is like question number 2, where you're given a specific amount of energy that you're going to be working with. And in questions like this, let's read it here. Suppose in the icy hot lab that the burner transfers 325 kilojoules of energy to 450 grams of liquid water at 20 degrees Celsius. What mass of the water would be boiled away? So we're looking to figure out a mass of water that's going to be turned into steam based upon a set amount of energy that's being added. If we draw our heating curve for that, temperature here, energy down here, then the water, which starts at 20, warms up until it starts to evaporate. And we know that it's going to happen at 100 degrees. So we have to warm up the liquid, and then we have the evaporating taking place. Well, not all of the water is likely to evaporate because some of the energy is going to get used up in this part right here, this first step. The warming is going to use up some energy. So only some of the energy is going to be left in step 2 to figure out the mass of substance that is actually going to be being boiled away. So in questions like this, where you have a set amount of energy that you're working with, as you go from step 1, step 2, maybe a step 3, you have to keep track of how much of the limited energy you have left to work with. So let's start work on this one and see what we end up with. Now remember, the first step here is that we're going to be warming up the liquid. So that's going to be Q equals mass times the heat capacity times the change in temperature. Well, how much energy is it going to take to get all this water up to boiling? That's what we need to figure out first. So the mass of liquid is 450 grams times the heat capacity times, let's see here, the final temperature is going to be 100, and the initial temperature was 20 degrees. So if we crunch that out to the correct number of significant figures, we get 150,000 joules of energy. So that is how much of the 325 kilojoules of energy has already been used. So how much energy do we have left? Well, what's the difference between them? If we convert that kilojoules to joules, we'd have that minus 150,000 joules, and that means that we only have 175,000 joules of energy left to boil the water. So now that we know how much energy out of our set amount, again, we only had that much to warm up the water, or to do for this whole process. It took 150,000 to get it to the point where now it can boil. So we have 175,000 joules of energy left for the boiling part of this. So that brings us to step number 2 then, which I'll do in a different color here. Step 2, this is the boiling part. So Q is going to equal mass times the heat of vaporization. Since we want to know what mass of water boils away, I would solve for the mass in this case. So I know that I've got this much energy left to boil away some mass of water, and that the heat of vaporization for water is 2,260 joules for every gram. So we need to isolate. That cancels out. 2260 over here. And to 3 sig figs, which is what we have left from the 175,000 joules, the answer comes out to 77.4 grams boil away. So in this style of problem, again, we have a set amount of energy. We have to go step by step through the problem. How much energy have we used up? Keeping track of how much we have left to work with. And then when we get to the final step, what is it that we're looking for? In this case, it was what mass of the 450 grams of water does boil away. We solve for that here, and it's 77.4 grams have boiled away. It is imperative that you do these little heating curve drawings beforehand to figure out what steps you need to take. What's going to happen first, what's going to happen second, what's going to happen third. Label the diagram like we did here. Label the diagram just like these, okay? Number it, what's going to happen first, what's going to happen second. The more organized you can make a problem, the easier it's going to be to figure out what to do next, okay? So there's questions 1 and 2. You've got questions 3 through, I don't know, I lost the second page, 3 through whatever is left to do for your assignment for tomorrow. 3 through 7. So work on that. You'll be whiteboarding them tomorrow. I'll have an answer key so that you can find out if you got the answers right or not. And then we will take questions on the assignment on Monday. We'll review all these heating problem things, LOL diagrams. We'll review everything on Monday when I get back. And then Tuesday is going to be your quiz. I talked about the quiz earlier. Your quiz is going to be on Tuesday. So make sure as you're working on it, if you still have questions, come armed with questions on Monday. Got the rest of the hour to work. Good luck.